So hopefully you concluded that the relative humidity will increase with height in this rising plume. And that's because the saturation vapor pressure drops, whereas the moisture content of the air is fixed. So it's got the same content, but the maximum possible value drops off, and so this ratio of the water content to that maximum increases. Now, of course, that means at some point it reaches a relative humidity of 1, and that is the point at which saturation occurs. So the air at that point cannot possibly hold any more moisture, and it can't even hold the amount of moisture it has. So it forces condensation of that moisture into liquid. And this height at which this occurs is known as the lifting condensation level, or LCL. Now you can solve what that is, if you wish, from the saturation vapor pressure equation here, because you're just finding where that saturation vapor pressure equals the moisture content of the air, which you can write as the surface humidity multiplied by the saturation vapor pressure at the surface. So if you go ahead and solve that, you'll find you get a prediction for this height at which saturation first occurs. We can plug in some typical numbers over the ocean. So you've got your ideal gas constant, typical temperature of about 20 degrees, your latent heat of vaporization, your molar mass of water, and your lapse rate, which we've discussed, and then a relative humidity over the ocean is typically about 0.8. You'll find that you get a lifting condensation level of about 600 meters. So this means if you have convection occurring over the ocean, on average, that's going to lift this moisture up to a height of 600 meters above the surface before it starts condensing into clouds.